Hi everyone, welcome to part 3 of differential equations. So far we've looked at first order differential equations in the form dy dx equals f of x and dy dx equals g of y. So that's where we've either got just x or just y. Whereas today, in this lesson, we're looking at differential equations where they have both. So things are about to get a little more hectic, but let's jump into it by first looking at the direction fields. So to help us understand this, let's talk through a specific example here. You don't need to write it down, but we'll just discuss it. So dy dx equals 2x over y squared. So we can see this involves both x and y. Let's start with something easy. Let's consider what happens when x equals 0. So we can see when x equals 0, this whole fraction will equal 0. So that means that when we graph our little lines for our direction field, everywhere where x equals 0, so along the y-axis, we're going to get horizontal lines. What about y equals 0? Well, because that's on the bottom, on the denominator there, we can't have y equals 0. So I'll just clarify that in this case, we can't have y equals 0. The derivative just doesn't exist there, so to speak. Alright, let's move on and have a look at what happens at x equals 1, because so far it seems okay. So when we substitute in x equals 1, we get two lots of 1, so 2 on the numerator, but then we've got y squared on the denominator, so it's not actually going to be the same all the way along x equals 1. It's going to change. Each individual point is going to be unique, and that's why these direction fields are a little bit more hectic. So if we fix x equals 1 in place, and we just start to focus on different y values. So let's have a look at what happens when y equals 1. Well, the derivative will be 2 over 1 squared, so that's 2. And so we can draw in our little gradient of 2 there. If we consider y equals 2, we're going to have 2 squared on the denominator, which is 4, and 2 over 4 simplifies to 1 half. So now, if we consider the point at x equals 1, y equals 2, we've got a much flatter gradient. I'll try and make that look a little bit flatter than this gradient of 2 here. And as we go upwards, right, through the y values, that denominator is just going to get bigger and bigger, so we're just going to get flatter and flatter, almost to 0, essentially. If we consider what's happening down at the negative y values, because we've got y squared on the bottom, it's just going to be like a mirror image. So when we substitute minus 1 in here, we get minus 1 squared is still just 1, and so our derivative will be 2. Likewise, if we substitute it in minus 2, etc., etc., so we get a mirror image. So there's a gradient of 2, then a gradient of a half. That probably should be a little bit flatter, and then it just keeps getting flatter and flatter and almost to 0. But what a mission, hey, to draw a direction field for this thing. So we're actually going to use a bit more software for this, so we'll jump over to Desmos and have a look at that. So this is a slope field generator in Desmos. I'll provide a link for you so you can have a play around with it yourself. Here's our function, or our differential equation I should say, 2x over y squared. And you can see this nice looking direction field here. It's going from minus 10 to 10. Now here is actually the function, or the family of functions rather, that satisfies our differential equation. So it's the cubed root of 3x squared plus c. So we know when we go through the integration process we end up with a plus c. Currently it's set to 0. This gives us a little indication of why we can't actually find the derivative here. I mean, look at that point that it comes to. there's going to be multiple tangents that you could run there. So that's why we don't get a derivative at y equals 0. And following the direction field, we can see how different functions would work. So I'll adjust the constant c so you can see up here how the curve follows the direction field. And if we actually get negative c values, that's pretty cool, hey? Now also, I'll just pause there, have a look at what's happening at y equals 0. Our curve, our function, is going vertical briefly. So once again, that's an undefined gradient. Okay, but how do we actually come up with this solution, this function, algebraically? Let's go and have a look at doing that now. We can solve differential equations in this form by separating the variables. And so what I mean by that is we want to get dx and x on one side and dy and y on the other side. So if we start with a differential equation in the form dy dx equals some function of x times some function of y, what we can do is just do a little bit of rearranging. Remember, we can treat this like a fraction. Okay, so we're going to multiply the dx over to the right hand side, and we are going to divide both sides by this g of y. Okay, so I'll write that as 1 on g of y over on the left. We've still got dy here, and then over here we've still got f of x on the right, and we now have dx attached to it. And so if we separate the variables, we can then go ahead and integrate both sides. So let's do that for the example that we were looking at. First, we've got to separate the variables. So we're going to take this y squared and multiply it across, and we'll take the dx and multiply it across, cross multiply. So y squared dy on the left, and 2x dx on the right. And then, like I said, we can now integrate both sides. And finding the integral of both of these functions is something that we can do. Let's give ourselves a bit more room here. Okay, so the integral of y squared. Well, we know that that is going to be y cubed on 3. And the integral of 2x, that's just x squared. Now, what about the constants, you ask? Well, good point. We need to add in the constants. However, the constant here is not necessarily going to be the same as the constant over here, is it? So we're going to show that they're different by using little c1 and little c2. Okay, let's get y by itself to actually find out what this function is. Now, when we subtract this constant from both sides, we just get a new constant, don't we? So c2 minus c1 is just going to be some other constant, right? Call that c3. And we'll keep going, multiply both sides by 3. When we multiply by 3, we get 3 lots of this constant c3, but that's just going to be another constant again, isn't it? So when we do our final step, which is taking the cubed root to get rid of that power of 3, we have the cubed root of 3x squared plus, this is just another constant. So now we'll finally go to what we're used to, a big capital C, and there is our answer. Flicking back to Desmos, that's what we saw, right? Okay. So, one thing to keep in mind though is not every differential equation is actually separable. So I'll give you a little example of one now before we continue. So let's say we had dy dx plus sine of x equal to xy. So it involves both x and y, this differential equation, and if we sort of played around with this a little bit and we say subtracted the sine x from both sides, looking at this right hand side, how on earth are we supposed to separate the variables? You know, like this y that's attached to the x. I mean, if we looked at multiplying everything by y, then we're just going to get a y attached to the sine of x. So that's not going to work. So we can't actually separate this one. So just something to be aware of. Okay, on to another example. So part A. Can we find the general solutions of dy dx equals 3x squared y, where y cannot equal 0? Now remember, in this case, y cannot equal 0, not because it's on the denominator or anything like that, but if y was equal to 0, then the derivative of 0 is just 0. That would satisfy this, but it's a very trivial solution. So we're not after that trivial solution. So they've stated that y cannot equal 0. Okay, so let's get into it. We need to separate the variables. So we have y on the right hand side, so let's divide both sides by y, and then we want to multiply both sides by the dx, and now we have just y on the left and just x on the right, and then we can integrate both sides. So let's just chuck our integral signs in here, be a bit cheeky. Left hand side, what is the integral of 1 on y? Well, hopefully you remember that this is the natural log of the absolute value of y. We have discussed this before. I'll provide a link to a good video that Eddie Wu put up if you want to have a look at that again. Right? Why is it that we get the absolute value when we're integrating the hyperbola function? Now we're going to have a constant of integration. Right, we'll call that C1. Over here on the right hand side, when we integrate, we get x cubed, and we have another constant of integration. Let's get y by itself. So we'll subtract the first constant from both sides, and so that will just give us some other constant. Right, we'll call that C3 again. And now to undo the natural log, we need to take the exponential of both sides. So we get y equals e to the power of x cubed plus, okay, I'm just going to call this c now, this constant. But remember, we can sort of undo that multiplication / addition index rule. So we know that when we have some a to the m times a to the n, that we can add the powers. Let's just undo that, right? Let's go backwards from this to this. So we have our e to the power of x cubed times by e to the power of c. But e to the power of c, it's just a constant. It's another constant. So let's call that a, put it out the front, and there is our solution. Y equals a times e to the power of x cubed. Okay, part B. Find the solution given the point 0, 1 lies on the function. So we found the general solutions before. Now we're after the specific solution. So just rewriting our answer from part A, we need to substitute in x equals 0 and y equals 1. So what happens when we do that? Well, we get e to the power of 0 cubed. Now 0 cubed, I could write the cubed, couldn't I? But 0 cubed is just 0. And what is e to the power of 0? Well, anything to the power of 0 is just 1. And so we have 1 equals a. Substituting that back in, that means the solution we are after is simply y equals e to the power of x cubed. And that's our solution. Now, if you'd like to have a little bit more of a look at that question graphically, I'd encourage you to use the Desmos software that we saw before. Alright, that finishes us off for today's lesson. Thanks for watching, and I'll see you next time.